This is Jack Hicks, and this is my report for Physics 2211 Lab 3. So the objectives were to create two computational models, one that simulates the orbit of a star around a black hole and the other that simulates a spaceship orbiting around a planet and a moon in a figure-8 motion. And the final result was to estimate the mass of the black hole in part 1, and then also to find an appropriate velocity which creates the correct orbit and does not crash the ship for part 2. So the main ideas for this lab were Newton's first and second law, the first law being that an object in motion stays in motion unless acted upon by an outside force, and the second law basically saying that an object's change in velocity is determined by the amount of force applied divided by the mass of the object multiplied by the change in time, which are those equations you see on the bottom right. And then the force in this scenario would be universal gravitation from different objects like a black hole or a planet or a moon, which is this equation right here. And we also have to take into account parallel and perpendicular forces, which added together give you the net force. And the parallel component being the change in speed of an object, and the perpendicular component being related to the change in direction of an object. And also, F net perpendicular is equal to mv squared over r, which is important later. So as a little introduction to the lab, part 1, we determined the mass of the black hole to be 1.14 times 10 to the 34th kilograms. And the system in that scenario was the star, whereas the surroundings were just the black hole and everything else, but it was just the black hole. So for part 2, an initial velocity of negative 15,000 meters per second in the positive x direction and 40,000 meters per second in the positive y direction were found to give the spaceship an irregular curving orbit, but achieving a figure-8 orbit was deemed to be close to impossible. And in this scenario, the spaceship was the system, whereas the surroundings were everything else. What models are we using? So we'll be using the model of Newton's second law, where using the Lab 3 starter code, we'll use a while loop to continuously update the force, velocity, then position of an object over specified time intervals. Now, in both parts, the net force was due to gravity, specifically universal gravity. It's non-constant, but part 1 included gravity only due to the black hole, whereas part 2 had gravity from the planet and the moon. And so we assume the only forces present were due to the celestial bodies mentioned above. So we have F net equals F net perp plus F net parallel, and then we update the velocity, and then we update the position using the known values. Now, we start with the known values of g, the gravitational constant, the mass of the star, and delta t, and initial and final velocities calculated based on email, which is something that the code did for part 1. Now, part 2 had the same gravitational constant, but different masses, masses of a planet, moon, and the ship, and our delta t then was 60 seconds. Here's the code. So here's the code for part 1, and as you can see, we initially solved for P initial and P final, which is momentum, based on the initial and final velocities given and the star's mass. Then we've calculated delta V and delta P, and then finally we calculated dP dt, which is just delta P over delta T. After this, we could get into the forces, F net being dP dt, which is given by Newton's second law, and then using F net, we found F net parallel and F net perpendicular to find all these components of the forces. Now, using these forces and the other known values, using the universal gravitation formula, we could calculate the mass of the black hole for each iteration, then dividing it by the number of iterations to get the average mass of the black hole, which is the estimated mass of the black hole. Here are the results from part 1 of the lab with the star orbiting the black hole and the vectors for F net parallel, and F net perpendicular, and the mass of the black hole on the right. Alright, so here's the code for part 2 of the lab, and as you can see, first you had to calculate F net on the moon due to the ship and the planet, then you had to calculate F net on the ship due to the moon and the planet, and then using Newton's second law, we would update the moon's velocity and position, and then the ship's velocity and position to get a nice orbit. Now, we would change the initial speed in the x and y direction to get an orbit in a figure-8 orbit, but that was deemed to be almost impossible, so our orbit was then just affected by both the moon and the planet instead of being in a figure-8. So here are the results from part 2 of the lab. As you can see, the orbit is not a figure-8 orbit because that was almost impossible to do, but you can see the irregular orbit because of the forces of attraction between the planet and the moon. And here are the orbital speed and period. Let's look at the data. Alright, so for part 1, we saw the star traveling in an elliptical orbit around the black hole, getting faster as it went closer to the black hole, and the parallel and perpendicular components of the net force increased as the star traveled closer to the black hole. Now, the mass of the black hole was again estimated to be about 1.14 times 10 to the 34th kilograms, and some error would just be how the code was calculated. And for part two, the spaceship first traveled in an elliptical orbit around the planet till it got close to the moon, where its orbit shifted slightly due to the force of attraction from the moon, and then it shifted again later on the cycle. So we found an initial velocity of negative 15 meters per second in the x direction and 40,000 meters per second in the y direction. And a figure 8 orbit was not achieved. An error could be due to infinitely many velocities that we could have picked, so I could have simply just chosen the wrong one, or human error in how the coding was done. So the difference between change in momentum and net force is that you can observe and measure change in momentum. However, you have to calculate net force. You cannot observe it. Now, what would you need to include in a computational model, including a system with a black hole, a star, a planet, and a moon? You would have to include all the force of attraction between the celestial bodies, the dominant force being the force of attraction with the black hole because it has the greatest mass.